The Fibonacci sequence is formed by the first two terms being 1, and any term thereafter would be the sum of the previous two. That means if we denote Fn as the nth Fibonacci number, then of course we have the first two to be 1, and also this recurrence relation. But let's say you want the 100th Fibonacci number, which is by the way pretty big. I don't think you really want to start by listing all the Fibonacci numbers from the start. So it would be helpful if we could find the general term of Fibonacci numbers, so that even if the general term is something crazy, it will still, hopefully, be better than calculating the 100th Fibonacci number from the start of the sequence. Turns out, the general term is not that crazy, and here, phi is the golden ratio, and this is known as the Binet formula. The most basic proof is just to check it. First, we check if it is true for n equals 1 and n equals 2. Then check whether the recurrence relation holds. Even though it is a valid proof, it is not very satisfying because it does not tell us where the formula came from. So we want to see the behavior of the sequence on a large scale, so that even if we don't know the exact general term, we can get the hang of it. If we plot a graph of Fn against n, then we obtain this graph. It is difficult to see whether it behaves polynomially or exponentially. So we plot log of Fn against n. And now we can confirm that it behaves exponentially. That means we can actually model it as a geometric sequence, at least approximately. So let's do that. Since we have the recurrence relation of Fibonacci numbers, we substitute our model. And now since both a and r are non-zero, we can reduce this equation to this quadratic. From the checking process, we have already explained why the two roots are phi and negative reciprocal of phi. Now we run into the problem. Which one should we take? Well, why not both? Modify the original form into this combined geometric series form. And now what remains is to solve for a and b. This is done by considering the first two Fibonacci numbers, then solving for a and b. This solving step is rather elementary and we gain no insight from this, so here is just the answer after solving. However, this is only slightly more satisfying because even though we know that it behaves like a geometric sequence, it certainly is not one, so why should we assume so in the first place? And why can we combine two geometric sequences together just because there are two roots of the quadratic equation? There are just some questions unanswered. Now that we know that the golden ratio is crucial to the general term, let's start playing with it. Golden ratio has this defining property. Now consider phi cubed. Then we repeatedly reduce the powers using the defining property of the golden ratio. Do the same for phi to the power 4 and phi to the power 5. Hopefully you can see the pattern here. The coefficient before phi as well as the constant term would be Fibonacci numbers. You can use mathematical induction to prove this more rigorously. What's more interesting is that apart from the golden ratio, there should also be another root of the quadratic equation. which we will call phi dash. Since everything we have done is only based on that quadratic equation, we should also have the corresponding equation for phi dash. That means we should see a similar pattern for phi dash. Now consider the difference of these two expressions. So now we can obtain an explicit expression for Fn. Now this proof is pretty satisfying, considering that it does not assume geometric sequence at the start. But there is just one very small problem. It is a bit strange that we consider the golden ratio in the beginning when it has no apparent relationship with the Fibonacci sequence. Yes, I am a tough critic when it comes to classic proofs. There is actually a proof based on matrix multiplication, but since maybe not everybody has learned linear algebra, I will put it in a separate video linked in the description. Now we will head over to the ultimate satisfying proof of the binate formula. First, we consider this series involving Fibonacci numbers. We have considered this series in the previous video, linked in the description. Note that the absolute value of x has to be sufficiently small. The exact range does not really matter here. Now multiply the series by x, and subtract the second equation from the first. The series after the x term is actually x squared times s, so by rearranging, we have this formula. But how does this help us? First, we separate this into two partial fractions. A, b, alpha, and beta are the constants that we want to find. We want to have the product of the denominators to be 1 minus x squared, which is the original one. And therefore, by comparing the coefficients of x and x squared terms, we have these two relations. Now we consider the numerator. Again, by considering the x and constant terms, we have these two relations. From the first relation, we substitute b equals negative a, and we get a in terms of alpha and beta. Since b is negative a, we also have b expressed. Going back, we now write s as shown, and we have the magical step. The geometric series has this formula, which can also be derived using a similar method to that of s. Therefore, we can write this fraction here as geometric series. And similarly, we rewrite the yellow boxed expression. However, notice how s is defined in the beginning. We now simply do some matching based on this red relation. Then we would have this formula as well. We just now have to solve for alpha and beta based on these two relations, and we would have the binate formula. This is a very good proof, but maybe since I bombarded a lot of mathematical facts to you, you may not be able to digest it, so I highly encourage you to pause and replay the proof we just mentioned to fully digest it. This is now a very satisfying proof. It explains why Fibonacci sequence is a combination of the geometric sequences pretty naturally through the partial fractions, as well as the relation to the golden ratio also naturally by the partial fractions. In fact, the technique used in the last proof is known as generating function. Let's say we have a sequence. The generating function of this sequence is defined to be a power series with the terms as the coefficients. Therefore, s as shown previously is the generating function of Fibonacci sequence. This technique is especially useful in finding the explicit general term of a sequence defined recursively. Of course, all the scales for satisfaction are simply my opinion. You have every right to deny all these and think that a particular proof is superior. But no matter what, we have gone through a lot of proofs for the binate formula today, and I hope you can gain some insights like I did when doing research for this video. As a content creator, I highly value your feedback and would like to gear more towards you, but I don't really know all of your math levels. For example, if most of my viewers have already learned calculus, then I can skip those parts and produce more advanced contents without worrying. On the other hand, if most viewers do not know a particular topic, then I know that I need to briefly introduce that topic before moving on to the focus of the video. So I hope that you could fill in the Google form linked in the description to help both you and me by helping create content more catered for you. Subscribe if you want more of these math videos, and give it a like if you enjoyed this video. See you next time!